So first of all, remark, I planned 4-hour lecture. Actually, these are just 3 hours, so I will make a big mistake. So to make 2 lectures in one, in 45 minutes. I know that this is a mistake, but anyway, I love to take risk. So yesterday I ended my, and of course there will be very few details. Yesterday I ended my lecture speaking about characteristic P. And I would like to remember that if F is Fp bar of B and X over F is an isotrivial curve, I constructed the example of points Pn such that the height with respect to the canonical bundle of Pn divided by the discriminant of Pn is going to plus infinity. So no Vojta type inequality is possible in this context. And another thing I would like to mention is that in Vojta inequality, it is something like height with respect to the canonical bundle of P less or equal than 1 plus epsilon discriminant of P plus O of 1. But I will not give details, but there exists example of non-isotrivial curves such that the lim, I think of hkx of P divided by h by discriminant of P is strictly bigger than 1. So this in characteristic P. So this example I'll do to Volok. And I think that this example are very important because first of all says that you have to be careful to the constant you put here. And second of all is you remember that in that the Vojta conjecture is related to the ABC conjecture. And if you believe that the order of difficulties of Diophantine geometry is function field of in characteristic 0, function field in characteristic P, and then number field, you start to worry about conjecture strong ABC conjecture over number field. So this is why my plan was to describe this example, but anyway, I just want to say this example exists and be careful about these things. But nevertheless, Mordell conjecture holds in characteristic P. What I mean is if XF is a theorem, if XF is a curve of genus G bigger or equal than 2 over F, and you have that xf of F is infinity. This is implies that xf is isotrivial. And this is not just a straightforward proof, copying what we saw yesterday. Yesterday we saw a proof of a Vojta type inequality for a variety with ample cotangent bundle, which in particular, using the version of Northcott we quoted in the first lecture, imply that for curves in characteristic 0 over a function field, this statement is true, because you will have that the height must be you cannot have that the height is going to infinity, so the height must be bounded, and then we saw that this implies that the curve is isotrivial. But in characteristic P, the point, I want to say just a word about the proof, is you how can you say, steps of the proof. First step, you prove Vojta type inequality, which is height less or equal than a constant time the discriminant. And this constant, you prove that depends only on G. And this can be done. You prove this under the hypothesis that Kodaira-Spencer class is not 0. Second step, you suppose that there are infinitely many points with bounded height. And this tells us that xf is dominated by an isotrivial curve, okay, and you prove that this implies this thing, and then you work a little bit. In the case of curve, you can deduce that xf is isotrivial. Third step, you suppose that the height of the points is going to impute plus infinity. You apply 1, and you deduce that the Kodaira-Spencer class of xf is 0. But this is not enough to obtain that the curve is isotrivial, because in characteristic 0, in characteristic P, this is not isotrivial, but you prove that Kodaira-Spencer class, for step, Kodaira-Spencer class of xf equal to 0 implies, or is equal essentially even, okay, implies that you can have a spec of f, spec of fp. Fp is simply the power, the p powers inside f, and you have xf, and there exists something I will call it xfp, and you prove that the Kodaira-Spencer class equal to 0, then it means that xf is not defined over f, but it is defined over the p power, which is a smaller field. Fp and this is a field because we are in characteristic p. And now you start again. You start again your all the points here will give points here. So you will have that xfp has infinitely many points, are the same genus. So xp is exactly in the same hypothesis of your curve. So you can do it again, and you will have that. So you will obtain that either isocitriviality of xfp, or xfp, let me write, is defined over xfp square. And you go to the infinity, and you will find that xf is defined over the intersection of fp to the pn, and this is the base field. So this is the main difference. This step is completely new with respect to characteristic p, characteristic 0. Characteristic 0, essentially it is enough to stop here, and in characteristic p you need new argument. And many of these arguments work because in characteristic 0 you can repeat, in characteristic p, sorry, you can repeat the hypothesis of this variety. The topology, let's say, of this variety is very similar to the topology of this variety because you have a unique minimal model. But if you work for variety in higher dimension, you have some problem in many places. I just want to say that recently Rosler and Gillet proved a similar statement for variety with ample cotangent bundle in characteristic P. And actually, essentially, they did this argument for ample variety with ample cotangent bundle in characteristic P. So, I think that this is enough for characteristic P methods, and I just want I want to point out one thing is this thing is quite interesting because it shows that you can, if you do the converse, you can see that if you start from a variety defined over Fp and then you pull back to F, you can prove that there exist varieties over F which are non-isotrivial but with zero Kodaira-Spencer class. So this very useful tool of Kodaira-Spencer class is very, you have to be careful in characteristic P. Okay. End of lecture 3. Now we start the last lecture. to question, if you have a question, but okay, I would like to speak about now relation with hyperbolicity. So we move from characteristic P to almost differential geometry. But, okay, why I want to speak about relation with hyperbolicity? Because I can imagine that varieties are, you can say, there are varieties which are rational, which are who have many algebraic points, too many. And is essentially difficult to see a structure. A structure means control the algebraic point by the discriminant, control the height of algebraic point by the discriminant is essentially impossible on Pn. On Pn you can find rational curves with arbitrarily high degree. And on the other side, really the very other side, we saw that we have varieties with ample cotangent bundle. And we see that here we can find Vojta type inequality. And then you have all the varieties which are in the middle, and somewhere here you have, from here on, you have a variety of general type, and then from here on, variety which are even not of general type. So the strategy would be, okay, we can do everything from here, and we would like to understand all the variety of general type. Try to understand variety which are not with this property, but almost. And from my point of view, the variety which are just nearby is hyperbolic variety. Is the variety which are almost in this class, but they are not in this class. So what are hyperbolic varieties? Okay, keep this diagram here. No. Oh, no. So we saw yesterday that X is with ample cotangent bundle implies that that if L is an ample line bundle on X, we can find there exists a constant A such that for every curve Y and for every morphism alpha from y to x, we have that the degree of alpha up a star of L is less or equal than a to g of y minus 2. And I will call this property algebraic hyperbolicity, AH. And in some way, we would like to move a little bit from this class to class of variety, which verify this property, and this property is weaker than this. So we would like to study varieties of this kind and study the arithmetic of this. And as I said, it is natural to try to do this. Just to understand, suppose that xf, so now f is again a field in characteristic 0, and I have xf over spec f, a variety, and a variety, and then I have a model. This is a model. And suppose that for some reason you know that x is AH. So x verify this property. The model, not the generic fiber, the model. Then you simply apply this inequality and you find that xf verify, let me call the Vojta type inequality. So till now, in the lectures until today, I didn't really care about what kind of model I am interested in. But here we start to see, to think that perhaps to look a little bit better to the models may be interesting. So, in some way, if some miracle says that xf is algebraically hyperbolic, I solved my problem. So let's try to understand if we can, in some way, study this kind of varieties. And the introduction is, and the thing is that we will study this variety, understand them from a point of view of differential geometry. And I will give the following definition. So let x a smooth, okay, to simplify, compact projective variety over C. I will say that x is Brody hyperbolic, BH, if every map from C to X is constant. And one find that the following facts. Let me take, otherwise I forgot. If dimension of x is equal to 1, Brody hyperbolic is equivalent to, say, genus bigger than or equal than 2. Second fact is no, analytic. If we have a map F, a map P from X to Y, and Y is Brody hyperbolic, and for every t in Y, p minus 1 of t equal xt is Brody hyperbolic, then x is Brody hyperbolic. This is very easy to prove. You take a map from C to X, then if you compose with pi, it must be constant, so it must be contained in a fiber, but if a fiber is hyperbolic, you cannot have this map. Third thing, and this requires a little bit of work, is Brody hyperbolic, compact, implies algebraic hyperbolic. So this tells us quite, well, yesterday we saw a little bit better, but anyway, just think about this. This tells us that, for instance, this general fact tells us that if you take xf over f, a curve, such that the model over b is smooth. Smooth means every fiber is smooth. Then xf verify a Vojta type inequality. Because you can, up to make a base change, anyway, the Vojta type inequality do not care too much about base change. Up to you can suppose that B is a curve of genus bigger than 1, strictly bigger than 1. Okay, sorry, genus of xf bigger than 1. Then this will be a family of, this will be a morphism where the base is hyperbolic and the fibers are hyperbolic, so the total space is hyperbolic, and so you can apply it 0.3, and so you can apply this, and you obtain that this curve, verify a Vojta type inequality. You don't know a lot about this constant, but anyway, doesn't matter. This is telling you, for the first time, this is giving to you a proof where you really look to the model, not just there exists a model. You look to the properties of the model. And you see that the problems are arriving from bad reduction. And by the way, if you look to the proof of McQuillan of the Vojta conjecture of a function field, is bad reduction is giving the main difficulty of the theorem. But there is also another property I would like to quote. No, I will not. Okay. There is also another definition which refines in some way the Brody hyperbolicity, which I will not explain too much, is that you can even do better, is what is called, there is another definition, is Kobayashi hyperbolicity. I will make a picture to explain this, because otherwise it takes too much time. You take a variety, and you take 2 points, and then you take a sequence of disks, holomorphic disks, inside these 2 points, inside this variety. And then what you do is you fix some points inside this disk, and you look to the hyperbolic distance from this point to this point, then the hyperbolic distance from this point to this point, and so on. And the hyperbolic with respect to the metric on the disk, the hyperbolic metric on the disk. And then you call this number, you call it, so this sequence of disk, you call it C, dc x, y. And then you consider the inf between all the possible sequence of disk, and this call it distance hyperbolic from x to y. And this is what is called the hyperbolic pseudo-distance inside a variety. And you say that a variety is Kobayashi hyperbolic if the hyperbolic pseudo-distance of 2 points is always positive. And what happens is that the main things to remember is the variety C is not Kobayashi hyperbolic. And why I say this? Because you have the following facts. The following fact that first, if x is Kobayashi hyperbolic, then it is Brody hyperbolic. And second fact is if x is compact and Kobayashi hyperbolic, then x is Brody hyperbolic and compact. And this is so. This definition of Kobayashi hyperbolicity is a little bit, let's say, more local than the Brody hyperbolicity, and I would like to give a last definition. I would say that suppose that U is an open set inside a variety X. So I can look to Kobayashi hyperbolicity here and Kobayashi hyperbolicity here, and I will say that U is hyperbolically embedded in X if, so I have, you have two sequence of point xn and yn in U, and you suppose that xn converges to x in x, and distance, hyperbolic distance with respect to U of xn and yn converges to 0, then yn converges to x. That means in some way that the hyperbolic embedding of the embedding of U of in x in some way preserve the hyperbolic metric, and also and this is in some way a weaker version of hyperbolicity. And why I introduce this? Because let's look to this example. If you take a curve xf over spec f curve, and you take the model, it may happen that x contains rational curve. This is due to the fact, or even elliptic curve. This is due to the fact that you can have some point here such that the fiber is singular. So you will not hope in general that the model is broadly hyperbolic, because it contains some rational curves, so it contains some map from C to your variety. So you want to weaken this property of being or having a model which is broadly hyperbolic. You want something which is weaker. But what is the situation here? The situation here is that you have xf, spec f, then you have, let's say, an open set like this. You are in this situation. Here you have an open set where here you always have this morphism is smooth. And this open set, you can always suppose that the base is hyperbolic. So this will have hyperbolic fibers. So this part will be hyperbolic, but this will not. So you have an open set where things are good, but you have some special fibers where things are not good. And you would like to use this property in this context. And what you have is the following theorem by Noguchi. You suppose that B smooth, it is even more general, I will state in a particular case, projective curve. And you have a morphism from X to B, from X to B, which is an X, let's say, smooth projective. And then you suppose, first, that there exists an open set U in B, such that for every y in U, call it p minus 1 of y is hyperbolic. Second, xu, which by definition is p minus 1 of u, which is embedded in x, is hyperbolically embedded. Then you will not have a Vojta type inequality, but you have that every sequence of section Fn from Bn, from B to X sequence of sections has a converging subsequence. And this is good for studying at least rational point. Why? Suppose that you have a model which is in this situation. Suppose that the hypothesis of the theorem by Noguchi is verified, and suppose you have a sequence of sections, then the I of sequence Fn of Fn, remember a section is a point, so you can compute the height with respect to an ample line bundle, must be bounded. Why? Because you take this sequence of section, suppose that you have this sequence of, suppose that you can construct a sequence of section with height which is not bounded. You do it, and then you extract a sequence which is converging. But being converging means that even the height, which is computed as a degree of some line bundle, must be converging. Because, yeah, by definition, because it's being converging means that at some point you have in the same component of this hom, because otherwise it's not converging. So that means that the height is converging. But the fact that the height is converging, it means that the height must be bounded, and if the height is bounded, then you have, so if Fn is Zariski dense, then the generic fiber is isotrivial, because you find a Zariski dense sequence of points with bounded height. And then I must say that Noguchi proves that in the case of curves, you can always obtain this hypothesis. So this is a proof by Noguchi of Mordell conjecture of a function field. But I think that there is still some possibility to advance in this direction, because as I tried to convince you, the study of hyperbolic, the arithmetic of hyperbolic variety is what we can hope at the moment for in the Vojta direction. It's finished. Okay, thank you.